Alright, so let's talk about trends. Trends. I'm going to put up at the top corner over here, this is the periodic table. This is an outline of the periodic table. Okay? As you go across and as you go down. Alright. Now, the first thing that we should talk about is atomic radius. And the easiest trend to see is that as you go down the periodic table, you get bigger as an atom. Okay, so you're getting bigger and bigger and bigger and bigger, so atomic radius
but atomic
increases.
Radius it isn't like the...
Right? Yep. Isn't what?
It's just when the same shell expands. It's not like adding another valence electron, is it?
So an atomic radius is, so it measures from the nucleus, so there's a nucleus, all the way out. It's the measurement from there to the outside electron, so the valence electron. And the valence electrons are always held the same distance away from each other, at least according to our model. So the atomic radius is going to be the same. For all
no,
the
what I was asking is if, like, it's not because it adds, does it ever add a shell and that makes it
bigger?
Yeah.
Yeah. That's what happens when you go down.
Oh, yeah.
So as you go down the periodic table, each step along the way in the periodic table,
Oh, no, I meant
you get another energy shell, or shell in the atom. So you can draw, this is the first shell, right? Here's the second shell. Look at the size of the atom. Is it getting bigger? Yes. Every time you go down a shell, you get bigger. So this is just kind of by definition, since we have shells that are getting bigger, then the atom gets bigger. Okay, so that's kind of just when you have to kind of
when you go across.
Yeah, when you go across, this one's kind of difficult.
It's like it just grows, it doesn't add. Right?
Now this is the one that always gets people caught up.
I'll probably get caught up.
Alright? As you go across, you're staying in the same shell. Right? You're staying in exactly the same shell. So let's say that you've got this shell. I'm going to do the second shell. Okay. Say you're in this shell. You've already got 2 electrons in the core, right? So we're on the second row right here. We're right there. And we're going our way across. Right? The first electron is going to be added right there. Right? The next one gets added right here. Each time you're adding this electron, and you're going across the periodic table, you're also adding a proton. Right? So when you're adding the protons, and these electrons are added to the same shell, the protons are stacking up. They're getting more positive and more positive and more positive and more positive. It's like increasing the positive charge on the nucleus.
So every time you add a shell, you add a proton. Right?
We're recording right now, so
yeah.
Can you hold up?
Yeah, sure.
Okay. So let's see. So as you're adding and charging up and charging up and charging up and charging up and getting more and more positive charge in this nucleus, it's making it more attractive to these outside electrons. These electrons are just being added about the same distance away from each other. About. But as they start being added, and as this positive charge starts adding up, they get sucked in closer and closer and closer. And so they're going to get, this whole atom is going to get smaller and smaller and smaller. Okay? It's going to get squeezed in because it's those outside electrons that are added to the same shell along the periodic table are going to be more attractive.
You don't like lose a shell, it just gets smaller, right?
Yeah, as you go across, you don't lose a shell. You don't lose anything.
Okay.
In fact, all you're doing is you're just gaining more protons in the middle and more electrons along the outside. Okay? It's like adding, I don't know, what's it like adding? I can't think of a metaphor at the time. But you keep on adding and adding and adding these electrons on the outside about the same distance, and you're just adding and adding and adding more positive charge in here. It's making them more attracted. Okay? So they get squeezed in. It's more positive charge. Yeah.
So basically it's just becoming more compact, but the radius stays. The radius will get bigger, but it just becomes more compact?
No. The radius is what's shrinking. So here's from the center of this atom to there, to the outside. It's getting smaller and smaller and smaller. So it's now coming in more, it's coming in more. Okay? So as you go across the periodic table, each time you go from one element. So let's just do a really simple example. Let's say that this right here, we've got.
Sorry guys, I have to go through.
It's okay. We've got times 3 protons.
And the word silver is back on the bag with the Nike symbol on it. That's
Whose backpack is that?
I know. Who would have a silver backpack with a Nike symbol? Come on.
You guys
Okay.
are the Holy Grail.
Let's take this, a real example right here. Here's lithium, right? There's 3 protons in the middle. The next element over is beryllium. It's got 4 protons in the middle, times 4 protons. And right here we've got the 2 electrons right there. And now we've got these electrons on the outside. Okay? This one, now it looks bigger than lithium right now, but the thing is that now these electrons are going to be sucked in closer because they see that positive charge. They see one more positive charge on there, right? In fact, their effective nuclear charge is 1 more than lithium. This proton in the middle, this extra proton, is now sucking these electrons in more. So now instead of being bigger, is what you might think if you're adding things to it, it's actually getting smaller. I think it's the scale right. Okay, it should be a little bit smaller. Yeah, a little bit smaller. So now we've got these electrons that are being sucked in a little bit more. And then let's go to the next element over. The next element over is boron, where you've got 5 protons in the middle. Okay? It's going to be sucked in even more, because you've got these 2 electrons right here, in the first shell, but now you've got these 3 over here. And each of these outside electrons, each of these valence electrons, sees this positive charge in the middle and gets attracted to it. More attracted than it was right over here. Over here was a little bit attracted, over here not very much attracted, but over here it's getting attracted over there. It's getting pulled in, getting squished. So this shows you the trend as you're going from left to right on the periodic table. You're getting shrinking and shrinking and shrinking in these atom sizes. Okay? Does that kind of make sense?
Mm-hmm.
Sort of? Mm-hmm. Okay. So a question I might ask you, and that is just to, like the word problems I've been giving you on the homeworks and so forth, or in the in-class problems, where I give you 3 elements like silicon, phosphorus, and sodium. And I say, arrange these from smallest to largest. Okay? Arrange these from smallest to largest. We got silicon, phosphorus, and sodium. So if you look at your periodic table, you see that sodium is farthest to the left, so that's sodium over here. And we got what's in the middle, silicon, right? And phosphorus over here. So this is on the periodic table. This is what it looks like.
Sodium is.
They're all in the same row.
It's
So
the same.
P is first.
So which one is the smallest? Let me ask you that.
Phosphorus.
Phosphorus.
This is the smallest, yes, because as you go across the periodic table, it gets smaller.
And then as you go up, it gets smaller.
What the exact reverse, Ben? Okay, as you go this direction, it
No,
gets
up,
bigger.
up.
You go up, it gets
Smaller.
yeah, right. So if you're going to rank these from smallest to largest, it would be phosphorus, silicon, sodium. Okay, that's it. And I might ask you to kind of like explain why this is, using that charge in the middle. So remember that as you go from left to right on the periodic table, you're adding more and more and more nuclear charge, which then sucks those valence electrons in. Those valence electrons are all in the same shell. They get sucked in towards that nucleus. Okay? All right. That's atomic radius, and we can say atomic radius On this side, atomic radius decreases
Wait, that's not the thing.
as you're going across. As you're going across the periodic table, maybe I'll do it this way. Atomic radius decreases. Okay? And what else? What else? What else? Ionization energy. Remember, ionization energy is the energy it takes to rip an electron away from an atom.
Opposite.
No, it follows atomic
Okay,
radius.
it follows on the left side, but not on the right. Not across, but it follows down and up.
Let's look. Atomic radius, as you go down, is it harder to pull off an atom
No,
that's really
It's
big?
easier.
It's easier.
It's easier. So the energy you need to put into it goes down. So the ionization energy decreases. And over here, as this is going down, this is getting smaller and smaller and smaller. These atoms are getting smaller and smaller and smaller as you go across. It's getting harder to pull them off. So its ionization energy increases. Yeah. Good. And the reasoning for that? Remember that?
It's like the iPod thing.
It's the iPod thing. What's the iPod thing?
It's like if you're holding an iPod or whatever closer to your body, it's harder to rip away than it is if you're holding it like 4 feet in front
It
of you.
takes more energy.
Yeah, it takes more energy to rip that, whatever you're holding in, close to you, away from you. And if it does, if you're holding it all the way away from your body like this, it's really easy to knock it off. Same thing is true for electrons. They're really, really attracted to the nucleus, then it's going to be harder to rip them away, so you're going to have to invest more energy into it. So the ionization energy will go up. Right? Alright. And the last trend that we have is electronegativity. Electronegativity.
Or electron affinity.
Or electron affinity, yes. So as you go down the periodic table, the electronegativity decreases. Yes. And as you go across the periodic table, the electronegativity increases. Electronegativity is an atom's ability to attract electrons, right? So this follows just in line with that nuclear charge and the size of the atom. Okay? If you've got a really strong charge, really high charge in the nucleus, it's going to be really attractive to passing by electrons. They're going to be attracted to that atom, to join that atom. Okay? But if you've got a really weak charge, it's just going to pass on by. It's not very attractive. It might be a little bit attracted to it, but not much. Okay? So it follows the same kind of idea as ionization energy. It's just exactly the opposite. It's how strongly this atom can attract something. Right? It's kind of the same idea as how strongly an atom can hold on to an electron. Right? Okay. So that's it, really. Those are the trends. And that's about it.
Cool.
What do we need to know for
Mendeleev.
Mendeleev? Mendeleev?
Mendeleev.
Yeah, Mendeleev. That guy.
We just need to know like the valence electrons.
Yeah. You just need to know that the main thing you need to know, the reason his theory is so powerful is that, no, I can do it, is that
In a second now.